One of the James Webb Space Telescope's science goals is to look back through time to when galaxies were young. Webb will do this by observing very distant galaxies, at over 13 billion light-years away from us. To see such far-off and faint objects, Webb needs a large mirror. A telescope's sensitivity, or how much detail it can see, is directly related to the size of the mirror area that collects light from the objects being observed. A larger area collects more light, just like a larger bucket collects more water in a rain shower than a small one. This is light years, and for more interesting videos, please subscribe to this channel. Webb telescope scientists and engineers determined that a primary mirror 6.5 meters, 21 feet 4 inches, across is what is needed to measure the light from these distant galaxies. Building a mirror this large is challenging, even for use on the ground. A mirror this large has never before been launched into space. If the Hubble Space Telescope's 2.4-meter mirror were scaled to be large enough for Webb, it would be too heavy to launch into orbit. The Webb team had to find new ways to build the mirror so that it would be light enough, only 1/10 of the mass of Hubble's mirror per unit area, yet very strong. The Webb telescope team also decided to build the mirror in segments on a structure that folds up, like the leaves of a drop-leaf table, so that it can fit into a rocket. The mirror would then unfold after launch. Each of the 18 hexagonal-shaped mirror segments is 1.32 meters, 4.3 feet, in diameter, flat to flat. Why hexagonal? The hexagonal shape allows for a roughly circular, segmented mirror with a high filling factor and 6-fold symmetry. The high filling factor means the segments fit together without gaps. If the segments were circular, there would be gaps between them. Symmetry is good because there need only be 3 different optical prescriptions for 18 segments, 6 of each. Finally, a roughly circular overall mirror shape is desired because that focuses the light into the most compact region on the detectors. Each of Webb's mirrors has an individual designation. A, B, or C denotes which of the 3 mirror prescriptions a segment is. Once in space, getting these mirrors to focus correctly on faraway galaxies is another challenge. Actuators, or tiny mechanical motors, provide the answer to achieving a single perfect focus. The primary mirror segments and secondary mirror are moved by 6 actuators that are attached to the back of each mirror piece. The primary mirror segments also have an additional actuator at their center that adjusts its curvature. The telescope's tertiary mirror remains stationary, keeping Webb's mirrors cold. One further challenge is to keep Webb's mirror cold. To see the first stars and galaxies in the early universe, astronomers have to observe the infrared light given off by them and use a telescope and instruments optimized for this light. Because warm objects give off infrared light, or heat, if Webb's mirror was the same temperature as the Hubble Space Telescope's, the faint infrared light from distant galaxies could be lost in the infrared glow of the mirror. Thus, Webb needs to be very cold, with its mirrors at around -220 degrees Celsius. The mirror as a whole must be able to withstand very cold temperatures as well as hold its shape. To keep Webb cold, it will be sent into deep space, far from the Earth. Sun shields will shade the mirrors and instruments from the sun's heat and keep them separated from the warm spacecraft bus. The mirrors for the James Webb Space Telescope were made of beryllium. Based on the expert team's recommendation, Northrop Grumman selected a beryllium mirror, and the project management at NASA Goddard approved this decision. Why beryllium? Beryllium is a light metal, atomic symbol, B, that has many features that make it desirable for Webb's primary mirror. In particular, beryllium is very strong for its weight and is good at holding its shape across a range of temperatures. Beryllium is a good conductor of electricity and heat and is not magnetic. Because it is light and strong, beryllium is often used to build parts for supersonic airplanes and space shuttles. It is also used in more down-to-earth applications, like springs and tools. The James Webb Space Telescope's 18 special lightweight beryllium mirrors had to make 14 stops to 11 different places around the U.S. to complete their manufacturing. Axis Technologies shaped the mirror blanks into their final shape. A beryllium mirror segment is 20 kilograms in mass. Once the mirror segments were shaped by Axis, they were sent to Richmond, California, where SSG/Tinsley polished them. At that point, the segments traveled to NASA's Marshall Space Flight Center in Huntsville, MSFC, Alabama for cryogenic testing. Cryogenic testing of the primary mirror segments began at Marshall's XRCF by Ball Aerospace in 2009. The change in mirror segment shape due to the exposure to these cryogenic temperatures was recorded. Together with the mirrors, this information traveled back to California for final surface polishing at Tinsley. The mirror's final polish was completed in June of 2011. Once a mirror segment's final shape was corrected and polished, a thin coating of gold is applied. Gold improves the mirror's reflection of infrared light. The typical thickness of the gold is 1000 angstroms, 100 nanometers. A thin layer of amorphous SiO2 glass is deposited on top of the gold to protect it from scratches in case of handling or if particles get on the surface and move around. Once the mirrors were completed, the science instruments were integrated into the telescope. At Goddard, the telescope also underwent environmental testing, both acoustic and vibration, to ensure it will be able to withstand the rigors of launch. Then, the telescope was sent off to NASA Johnson in Houston, Texas, for tests of the optics and instruments at cryogenic temperatures. NASA Johnson's Chamber A is the only thermal vacuum chamber NASA has that is large enough for Webb. Aligning the mirrors on Earth and in space. Once the telescope is in orbit, engineers on Earth will need to make corrections to the positioning of the Webb telescope's primary mirror segments to bring them ensuring they will produce sharp, focused images. These corrections are made through a process called wavefront sensing and control, which aligns the mirrors to within tens of nanometers. During this process, a wavefront sensor measures any imperfections in the alignment of the mirror segments that prevent them from acting like a single, 6.5-meter mirror. Engineers will use NIRCam to take 18 out-of-focus images of a star, one from each mirror segment. The engineers then will use computer algorithms to determine the overall shape of the primary mirror from those individual images and to determine how they must move the mirrors to align them. Engineers have already tested this alignment process in the cryogenic, vacuum environment of Chamber A at NASA's Johnson Space Center. JWST is currently on its way to its final destination in space. The second Lagrangian point, L2, 1.5 million kilometers, or 1 million miles away from Earth. Even with all the monumental success so far, there's little time for the Webb team to pause and reflect. Anyway, the telescope's revolutionary technology will explore every phase of cosmic history, from within our solar system to the most distant observable galaxies in the early universe, to everything in between. Webb will reveal new and unexpected discoveries and help humanity understand the origins of the universe and our place in it.